Welcome to this video on recognizing soundscapes in pod data, mainly FPod data. It is really useful because soundscapes can affect the detection performance of the pod itself. They can affect the distribution of the cetaceans, and it's very much part of trying to understand what it is we're looking at when we look at this acoustic data. Um, so here's some data from the Georgian team in the Black Sea Trends project, and you can see 110 days of data there. And if you look at the black line down at the bottom of the lowest panel, that's the number of clicks being recorded on average per minute. And you can see that it's quite a lumpy graph. And these lumps actually will be storms. They'll be, they're lasting over quite a few days or windy periods. So let's zoom in on this one here by dragging across. Um, so we have got some cetacean detections in there, but you can see these high numbers of clicks. So if we zoom in there, we see this kind of pattern of predominantly lower frequencies in this case. It's not a uniform noise pattern, it's got some grouping. And let's just zoom right in here. And this pattern here is very typical of sediment transport. A lot of weak clicks with a rather smooth profile at the top. So what's happening is waves at the surface, actually, there is some causing some movement of the sediments on the seabed, and we can zoom in even further, and there's the pattern. So I want to contrast that with what the actual detections of animals look like. So here we've got some dolphins. Maybe I'll move on a bit to where it's not quite so noisy in the background. Yeah, we've got some dolphins over there. So here, what you see is that these are dolphin detections, and they're more strongly grouped into packets, as I call them. They don't have that smooth profile that we saw with the sediment transport produced by the storm. And if we zoom in, we see a very nice click train. But another really significant thing we see is most of these clicks have got some multipath propagation. That's replicates of the click that arrive later at the pod, either because they've gone through a longer path being reflected off the sea surface, or they've just been bent this way and that through the water by differences in the sound speed in different parts of the water body. But you see quite a strong similarity in the multipath pattern there. That's an incredibly useful thing. And it's just worth mentioning that we've now got a utility which we will release, which will take a wave file recording at 500k samples a second or higher and convert it into a virtual FPod. But it can't work if you've used click snippets or whatever, because then you lose these little guys, the little replicates that are, just by looking at three of those, you can say, or you could say it's going to be a dolphin with almost complete certainty. Okay, so there's a sort of contrast between the continuous noise generated by the sediment transport and this packet noise from cetaceans. There's also another class of noise, of sort of transient noise, when for example, boats pass. So I should have an example of that here. So in this data file, you can see right in the middle here, there's a big upsurge in the number of clicks being um, recorded. And if I zoom in on that, this is what you see. If we look earlier, you see this is kind of noise in this region. And then suddenly this thing comes along and starts generating more noise. It eases a bit, then it builds up. Then there's a gap here, which is because the system has maxed out. In this minute here, it's already recorded at only less than 20 seconds in the maximum number of clicks it's allowed for that minute. And then in the next minute, it's not maxed out, the noise is fading away. This is very typical of a boat passing. And if you get detections in here, they're probably boat sonars or false. They're very rarely cetaceans. Um, okay, so there are a lot of much shorter noise bursts in the sea, and they are very difficult to understand and interpret. And I'm not going to say much about them, but you will see them in the data. Um, so we could now look at wave noise. Um, so where would that be? Here we are. So this is a pod in very shallow water. It's basically moored on a sandy beach below the tide marks, and it's in water that's only sort of 10 to 20 centimeters deep, and tiny waves are passing over it, and they're moving the sand and creating that pattern of sediment transport noise that we saw. And the frequency of this noise tells you, or is determined by, the size of the particles of sediment that are in movement. So sand particles that are about half a millimeter, no, a quarter of a millimeter in diameter, generate noise at about 130 kilohertz, which is where porpoises are. Um, but here you've got these other, much louder, lower frequency bursts, and this is these tiny waves breaking. So as they move in and out, the currents are moving the sand. And if you go snorkeling, you will have seen this. You know, you get little sand ridges, and if you're snorkeling in water that's like very shallow, you see these little swirls of sand off the top of the ridge. That little swirl of sand is extraordinarily noisy, and pods register it very easily. So these louder spikes, they're actually the bubbles associated with the wave that are breaking. I mean, the bubble is breaking. The wave also is breaking, of course. But bubbles, as they burst, create quite loud noises. So you've got two components to that kind of noise. So this is another example of packet noise. So in packet noise, I've got cetaceans, waves, fish tags, pingers, and other things that we can't always identify. That contrasts with continuous noise when the sediment transport has no gaps, and yeah, the shorter noise. So um, the the sediment transport, when it's happening more or less continuously, has a massive effect on the cetaceans because it does effectively jam their sonar. There aren't any quiet gaps in between in which they can kind of hear the echoes from their echolocation. So they will tend to move out. Here, it's not quite continuous, so if a cetacean were in water this shallow, it could operate its sonar in these sort of quieter periods. Um, okay, next we'll have a look at some severe noise. Um, So here we're looking at have I got the right one here? Sorry, I've got so many open that let's try this one. Yeah, this is the right one. We're looking at very rough weather, a pod moored in shallow water outside the harbour of the village Mosul where we make them. And if you look at the frequency display at the top, you can see there are kind of bursts of sound covering a whole range of frequencies. So you've undoubtedly got sediment transport, you've got breaking waves and bubbles, you've got the pod being rubbed against seaweed, rocks, and everything. Um, and in places it comes in bursts. So let's sort of zoom in on a burst here um, and zoom in a bit further. And you can see we've got some very loud clicks here. Um, but when we zoom in, they don't have that kind of repeated multipath that we saw earlier. So noise rarely has repeated multipath. Just occasionally you kind of see it and you wonder what on earth that source was. Basically, if you do see it, it was a loud distant source where the sound has propagated a long way to get to the pod and has followed different paths in doing that. Um, okay, let's actually look at some really good sediment transport noise here, because it is a big issue. So here we're looking at 18 days. You can see the pod actually isn't even in the water in the first 9 days, and the temperature is swinging up and down in a daily pattern, very typical of it not being in the water. The pod in its the Kerno classifier is making detections in here, um, and those detections, well, actually they're boat sonars. They could be right because it could be lying on the deck of the boat and hearing the sonar. But generally speaking, you have to rule out all detections before it goes in the water. Then it does go in the water, and we can see there are bursts of noise happening down here. Um, and yeah, if we kind of in these bursts of noise, there's more lower frequencies, so the sediments, if they're being disturbed, um, will be larger than the tiny sizes I mentioned earlier, a quarter millimeter diameter. So here we've got like a prolonged period of noise, and we've got some porpoises, so that will be fun. Let's zoom in on that. Um, and here, so what files have I got open here? I've got one copy of the FP1, two copies of the FP3. Okay, so we're seeing these bursts of noise right up at porpoise frequencies there. Yeah, 119 kilohertz. It's worth saying that pods generally report the frequency of porpoise clicks slightly lower than you would get from a Fourier transform. Um, okay, and there we've got a porpoise click train report. I'd really like to find one where we get the two things coexisting. Okay, so we'll look at amplitude now on the lowest panel there. So you can see the sediment transport, the blue grass here, with this kind of smooth profile. And here you can see a porpoise click train occurring at the same time. So in terms of frequencies, there's basically no difference. And if we zoom in, we kind of see a click train that is a bit louder, and we see this background sediment transport. It's actually very hard for the classifier to pull this out, and I'm wondering why it succeeded here. Um, there's no very obvious pattern of multipath from that porpoise, um, but you know what we do see is it is distinct in amplitude. It's got this nice regularity of click rate. Let's just look at the clicks per second to see if it's plausible. Yeah, it's not dead flat, so it's probably not a sonar. It's up about 120 clicks a second. This little dot tells you, white dot, where in the click the loudest cycle was. And that's very reasonable for a porpoise. So let's just look at the number of cycles in the noise. Um, and what you see there is that in the noise, this dot is occurring anywhere. It's not mostly in the middle of the click. And this is because these aren't even really distinct clicks. They're just segments of this almost continuous roar of 120 kilohertz sound coming from moving sand, and little sections have been picked out by the pod in real time because they are narrow band. Um, okay, so that's what sediment transport looks like. It's the main cause of errors for methods that are based on spectral analysis, because you can get sediment transport noise with an absolutely perfect porpoise click spectrum. Okay, another big bogey is shrimps. So I hope I've got some shrimps here somewhere. Um, no, okay, I'm going to have to open the file. I hope I can find it. Um, close all files, open a file set. Um, um, okay, so this is data from Ada Natoli in United Arab Emirates from a site off Dubai. And this is mostly shrimp clicks. It's not sediment transport. It doesn't have those nice sort of profiles. Um, oh, here we're looking at number of cycles, so you can see that the peaks are generally early rather than anywhere. I'll just change that to amplitude. Um, and that is a fairly horrific pattern of shrimp noise. Um, I'm not sure I've picked the right file here and whether it's actually got any. Okay, so here it's actually picking up a boat sonar. We'll just um, there it's claiming a dolphin detection, but it is one of those boat passes that we looked at earlier. Um, yeah, and here is some good data from a cetacean in there. I won't try and unpack that now because that'll be more in the data validation videos. Um, so a thing we should look at as well, which is kind of quite extraordinary when you see it. This is data from the coast of Kenya, thanks to Michael Wangombe, who set up an acoustic project there. And here we're looking at 18 days of data in the FP1 file. And you see this extraordinary repeated pattern. So people have understandably called this chorusing. It's a chorus with a lot of stamina because it's going from, where are we, 1800 hours to 6 in the morning. Yeah, and yeah, 1730 to 6:30. So we don't really know what is doing this chorusing. I mean, it's very interesting. This is a very dramatic example, but it's not rare. It's not exclusively tropical. We've seen it off the coast of Britain here. Um, and it would be great if we knew more about it. Um, just as a matter of interest, if you want to work out what the periodicity is, you can select this file for action, and then you can click the ac.f button at the top of the screen. Excuse me. And it's now working away at an autocorrelation of this large file. And although this takes a while, it is actually extremely quick because autocorrelation is a very computationally intensive process. And this does the autocorrelation over a very long time span. So I'm actually rather proud of this, but it looks like it might fail to work here. Anyway, please talk. Oh, that, that is an outrageously perfect 24-hour autocorrelation. So what an autocorrelation tells you is that if you've got a sound now, you know, if you've got whatever it is now, you're likely to have it in 24 hours, 48 hours, 72 hours, etc. And if you haven't got it, you're likely to not have it at the same periodicity. This is really useful for sorting out tidal cycles from DL cycles or 24-hour cycles. And it's also very useful for working out the duration of residence of animals at a site. How long do they hang around? Um, so we could actually do the same thing on the, if we select this file for action. So I've selected one of the, um, actually we just make sure it is just looking at dolphins. We're now looking at the autocorrelation on dolphins, and that is showing a distinct correlation of some sort. I won't go further into this. I just wanted to give you a kind of a taste of it. Um, so yeah, so that's it. That's chorusing. Um, that's the sort of main gist of this noise video. So the role of detecting multipath in looking at noise is quite valuable because cetaceans do make a lot of noise, and as we saw in the data from Georgia, they can kind of look a bit similar to storm noise, but when you zoom in, it's very different. And of course, generally speaking, the Kerno F classifier pulls out their click trains. Um, So, okay, that was recognizing soundscapes. Thank you for your attention.